all to this webinar on the occasion of National Mathematics Day, which is also being broadcast on IGNOU's official Facebook page and YouTube channel. As we know, National Mathematics Day is celebrated every year on December 22nd to honor the birth anniversary of one of the most remarkable mathematician of the 20th century, Srinivasa Ramanujan. Before he died at the age of just 32, he had already given the world around 3,500 mathematical formulae that scientists have still not been able to completely prove. The main objective behind celebrating this day is to raise awareness among people about the importance of mathematics for the development of humanity. Srinivasa Ramanujan, a self-taught mathematician, made extraordinary contributions to mathematical analysis, number theory, infinite series, and continued fractions. From compiling over 3,900 mathematical results and equations to getting discoveries named after him, his numerous assertions in mathematics opened up new fields of mathematical research. I now invite Professor Sujata Verma, Director, School of Sciences, to welcome the participants.
Good morning, everyone. I am Professor Sujata Verma, Director, School of Sciences and Faculty of Mathematics. Welcome you all to this event webinar on National Mathematics Day. I first of all welcome our Honorable Vice Chancellor of IGNOU, Professor Nageshwar Rao, and Pro Vice Chancellor Sir, Professor R.P.D. Das, Professor Satyakant, and Professor Uma Kanjilal, and Professor Sumitra Kukreti. I welcome all and my hearty welcome to our honorable speakers, Professor R. Balasubramanian, former Director of Institute of Mathematical Sciences, and Professor A. Vijay Kumar, Honorary Professor, Cochin University of Science and Technology. And I welcome both our eminent speakers to this event on National Day Mathematics program. And I am very thankful to them who have very kindly accepted our invitation to grace this occasion. And even with their very busy schedule, I welcome Professor Vijay Kumar sir, namaste, and Professor Balasubramaniam, namaste. Yeah, and I also welcome the mathematics experts who have very kindly accepted our invitation and be part of this event. I could see Professor Riddhisha and others, and I'm very happy to that you have all accepted our invitation and to grace this occasion. And now I thank my welcome. I almost thank my hearty welcome to all the directors and and head of the divisions and our faculty members of School of Sciences and outside School of Sciences, and my dear students. Many students also have participated in this event, and I welcome you all and my dear friends. Today, we have assembled here to celebrate National Mathematics Day. And Indian government has declared 22nd December to be National Mathematics Day, and this was announced on February 2012 to make 125th birth anniversary of Indian legend mathematician Srinivasa Ramanujan. Let me start with a shloka. Yatha shikha mayurana nagana maniyo yatha tadhara vedanga shastrana ganidam murdhani stita. The meaning is that just as peacock has crest and snake has gem, in the same way, mathematics has the best place in Vedas and Shastra. Actually, it has place every in real life situations and human mathematics all around. So, German mathematician Carl Friedrich Gauss said, mathematics is the queen of sciences, and number theory, in which Professor Srinivasa Ramanujan has a lot of legendary contribution and theories, number theory is the queen of mathematics. So today we are going to experience, or our speakers will take us to the beauty of number theory and other contributions of Ramanujan. And I'm sure that we all will be very enlightened with the journey of Ramanujan's mathematics. And we are going to have a very inspiring talk by our eminent speakers. And I especially take this opportunity to welcome all of you to this event, and I wish you all a very happy National Mathematics Day. Professor Nageshwar Rao will be just joining. He has accepted to inaugurate this session. He will be giving the inaugural speech. Professor Deepika, could you please ask him?
Yeah, I think he has not joined yet. So can we start this?
Yeah. So I think our Vice Chancellor will be joining. He is busy in 1 or 2 meetings.
Yeah.
And he said that I'll just join. And by that time, you can have the proceeding on behalf of Vice Chancellor. Again, I'm putting some flowers on Ramanujan on behalf of the School of Sciences. And I officially Professor, our Vice Chancellor will be joining us. Meanwhile, I think we can have our proceedings of the invited speakers. And I request Professor Deepika to introduce, and especially I'll give a brief introduction that Professor Vijay Kumar will be speaking on Srinivasa Ramanujan, the man who knew infinity. Infinity means Anantata. Anantata is a word that it's still very needs a lot of thinking to understand that. Is it endless, unlimited, or so? The man who knew infinity. So he will talk about that, and he has done a lot of popular mathematics lectures, and he is very eminent in popularizing mathematics. Even today, Malayalam paper, he has written a very good exposition on Ramanujan, and I'm sure that we are going to have a very enlightened speak for him. And our Professor R. Balasubramaniam, he's a Padma Shri. We are so honored with him for his mathematics contributions, and he is a number theorist, and he will talk on very legendary work of Professor Professor Srinivasa Ramanujan, circle method and further development method. And he will explain to you the beauty of number theory and how the importance of Ramanujan's work on circle method. I am really happy to have you, sir. And we are all looking for it. We will start with Professor Deepika. Would you like to?
Thank you, Professor Verma. Our first speaker in today's webinar is well-known mathematician, Professor Ambat Vijay Kumar from the Department of Mathematics, Cochin University of Science and Technology, Kerala. He's a fellow, Institute of Combinatorics and its Applications, Canada. His area of interests include discrete mathematics, graph theory, graph spectra and energy, distance energy, graph products, power domination, and complex networks. He is actively involved in school math education as well. He has been the regional coordinator of Indian National Math Olympiad since 1990. He has written many popular math articles, as Professor Verma also mentioned, in Malayalam and English. Today, he will talk on the topic Srinivasa Ramanujan, a man who knew infinity. Now, I request Professor Vijay Kumar. It's over to Professor Vijay Kumar.
Thank you very much, and a very good morning to all of you. Thank you, Professor Sujata Verma, who is a good old friend of mine.
Yeah, thank
We
you.
were
Thank you.
friends since 1985. And I've come to IGNOU campus for some programs earlier.
Yeah.
So today,
Thank you.
we are celebrating National Mathematics Day, the birthday of Srinivasa Ramanujan, birth anniversary of Srinivasa Ramanujan. And My objective of this presentation is to convince you all again why Ramanujan should be celebrated. There are several reasons beyond this 45 minutes presentation. Professor Balasubramaniam will talk about technical works of Srinivasa Ramanujan, his famous circle method. I am neither competent nor authoritative to talk about the works of Srinivasa Ramanujan. But what prompted me to talk about the man, Srinivasa Ramanujan, is that I was involved in the Malayalam translation of the book, The Man Who Knew Infinity, which we published in 2013. And I had the good opportunity to read the original book of Robert Canigal, The Man Who Knew Infinity, several times because I had to check the correctness of the facts of the Malayalam translation. So that made me closer to Ramanujan and a fan of Ramanujan also. And therefore, I thought I will popularize him as a person. There are several difficulties that he had in pursuing a career in mathematics, most of which is well known. And he was very badly in need of money. And that was the strong reason which prompted him to go to UK to do mathematics than doing accounting in Madras Port Trust. I will also appeal in my presentation that we should celebrate not only Srinivasa Ramanujan, there are equally or maybe less next level, there are several mathematicians we should celebrate, including C.R. Rao, S.R.S. Varadan, Srikhande, R.C. Bose, and so many. And in fact, when I taught National Mathematics Day lecture yesterday in a college in Tamil Nadu, some girl students asked me, why only Ramanujan? Why not these people also? So there's an appeal because I am talking to the audience in Delhi. They have more influence than that in Kerala. And I hope that sometime from next year, we should make children know the contributions of scientists and mathematicians of the country. So with these few words, let me first of all, again, thank you for this invitation. And I am going to start my presentation. Is it okay?
Yes, sir, we can see you.
Okay. So what is the title? I want to recheck. Please, some of you read it so that I am confident that...
Yeah.
Srinivasa Ramanujan, the man who knew infinity.
Very good. So this is the beautiful campus of Cochin University. Cochin University celebrates Golden Jubilee 50th year this year. And I have been in Cochin University in different forms, from first as a master's student, then as a faculty for the last 42 years. So Cochin University is dear to me. For the past several years, I start any presentation for anybody with a quote by a great inspiring teacher because of some personal reasons, who passed away on 27th July 2015. And whenever I used to give lectures on Srinivasa Ramanujan, I'm always reminded of the difficulties that Dr. Kalam had when he was a young boy. And we can compare, we can do some research on the initial life of Kalam and Srinivasa Ramanujan. They are all comparable at several levels. You cannot change your future, but you can change your habits. And surely your habits will change your future. I think that's a very correct wordings by Dr. Kalam. As I told in the beginning, we are celebrating as a tribute to natural genius Srinivasa Ramanujan, who was with us for exactly 32 days, 4 months and 4 days, from 22 December 1887 to 26 April 1920. And Kerala, through his Kerala Language Institute, is proud to say that when the then Honorable Prime Minister Dr. Manmohan Singh mentioned in 2012 the need for having the translation of English book by Robert Canigal, who is per se not a mathematician, he is a mechanical engineer and science writer and popularizer in Massachusetts Institute of Technology, who wrote the book The Man Who Knew Infinity. We translated this book to Malayalam with the caption Anandate Aranya Al, The Man Who Knew Infinity, and Anandam Endan Aranyal, second edition. We have sold out 5,000 copies. And before December 31st, we are going to make it e-version of this book. So I'm very happy that I could associate with this project, The Man Who Knew Infinity's Malayalam translation. I gathered several information from several people, so I am thankful to many of them. This is a photo of Srinivasa Ramanujan that you see, bit obese, but this obesity is not due to his heavy overweight, but due to malnutrition. And that is the photo which we have. We have seen only 1 or 2 photos of Ramanujan, which he took while applying for the passport. So this number, 1729, has a strong bearing on the life of Ramanujan, at least to popularize his mathematics. So keep this number in mind. I will come to this point later. Let me start with the quote by Jawaharlal Nehru in his Discovery of India. Ramanujan's brief life and death are symbolic of the conditions in India. Of our millions, how few get any education at all? How many live on the verge of starvation? So starvation and education are 2 phenomena which we could connect with Srinivasa Ramanujan also, because he had a lot of difficulties financially and he had no means to have food every day. So he was badly in need of money, and the quotation by Sri Jawaharlal Nehru is quite apt, because there are many places in India where children are denied of education and food. The quote by Bruce Byrne, one of the international authorities on Srinivasa Ramanujan, coming from University of Illinois, says, "The world of mathematics would be much different today had not Ramanujan graced his profession with a vast assortment of beautiful ideas, many of which continue to strongly influence contemporary mathematics research." This is a point which I would like to stress, that though Ramanujan passed away about 100 years ago, the mathematics influenced by Ramanujan still continues on areas which are not known or they're not existent even when Ramanujan was living. That says the greatness of Ramanujan. So I'll give you a timeline of Ramanujan. 22nd December 1887, as a son of Srinivasa Iyengar, who was an accountant in a textile shop, and Komarathammal, who was a housewife, also a singer in nearby temples. And his birth star is Uttaratavi. I don't know what is the corresponding thing in Hindi. And he was tremendously influenced by the book of George Carr in 1903, Synopsis of Elementary Results in Pure Mathematics. We could have seen people influencing people, or a movie influencing people, or our teachers influencing us. But I have not seen anywhere else a book influencing a mathematician, and later Ramanujan following the entire style of the full style of George Carr. He became a matriculate in 1904. In 1907, he failed in first degree of arts. 1909, he married Janaki. And 1911, first research paper in Journal of Indian Mathematical Society on Bernoulli numbers. And as I told earlier, he was badly in need of money. So he got a job as an accountant in Madras Port Trust, which obviously he was not at all satisfied. So I will show you the book of George Shoebridge Carr, who is a British mathematician, a synopsis of elementary results in pure mathematics, which was published in, I think, 1886. Digitalized new versions of this publication is available in the net. Let me continue. In 1913, he became the first research scholar of the University of Madras, and he wrote a historic letter to Hardy, which became a turning point. In our life also, there are several incidents which becomes turning points. I would strongly urge you all to read the book of Turning by the title Turning Points by one of my mentors, Dr. APJ Abdul Kalam, where he mentions about several turning points in his life. So this historic letter to Hardy became a turning point in the life of Srinivasa Ramanujan, so which made him travel to London by ship in 1914. And despite he was a failure in the formal education in India, because of his wonderful mathematics, in 1916, he was awarded BA degree by the most prestigious university in the world, even now, the Cambridge University, for his works on highly composite numbers, which went through 62 pages containing 269 equations, which appeared in the Journal of London Mathematical Society in 1915. In 1918, he was elected as the Fellow of the Royal Society, London, the first Indian scientist to become a Fellow of Royal Society, and also as a Fellow of Trinity College, London. And as you all know, he was totally unwell during 1919 and early 1920. And on 26th April 1920, he passed away at Chennai. Many books say that he passed away due to tuberculosis, but medical experts say that he didn't have any problem of tuberculosis, but he had a problem on amoebiasis. That is supposed to be the reason for the death of Srinivasa Ramanujan, who was with us 32 years, 4 months, and 4 days. Those who are not from Tamil Nadu, I just wanted to tell you where is this Namakkal. This is Coimbatore Road, Salem. Namakkal, this is the famous Namakkal temple that Srinivasa Ramanujan was praying almost every day. And you see Tanjavur, all these places which are nearer to Namakkal. His mother, the goddess Namagiri deity at Namakkal, and the town school Kumbakonam, where Ramanujan studied from 1898 to 1903. This is the birthplace in Erode, left, and his house in Kumbakonam. This is the Ramanujan's house, now kept by Shastra University as an international monument. I was fortunate enough to visit this place in 2014. You see a small house with a room, and I strongly feel that this blackboard was kept for tourist purposes. There is no chance that Srinivasa Ramanujan used a blackboard, which I will explain later why he could not do. And this is the photos and library of town Srinivasa Ramanujan's works, photos and all that from Town School Kumbakonam. And this is from Shastra University Museum. Here I want to spend a minute because one student, when I presenting this a couple of years ago, asked me a question, which I am going to ask you. This is the horoscope of Srinivasa Ramanujan, which was written in 1887. And the student of mine asked me whether any modern astrologist could explain whether this horoscope says that of a great mathematician. That was a very interesting question. So from this horoscope, can you predict that the owner of this horoscope will become a great mathematician? I couldn't give the answer, so consulted my astrologers in Cochin and showed this Jadagam or horoscope to them. And they are also told that they are helpless because we don't have the Panchanga of 1887. There is no meaning in going back, but still, we are as a researcher, I'm interested in knowing whether this horoscope contained that of a great mathematician. Something happened in the life of Srinivasa Ramanujan. He absconded from his house due to some reason, mainly financial reason. So on 2nd September 1905, the Hindu paper based at Chennai carried a news item, a missing boy. A Brahmin boy of the Vaishnava sect named Ramanujam, of fair complexion and aged about 18 years, was still recently a student of the Kumbakonam College. He left his home on some misunderstanding. The advertisement was given by J. Srinivasa Raghava Iyengar, his father, 18, Sarangabani Sannidhi Street, Kumbakonam. Those who have not visited Kumbakonam, I will request all of you to visit Kumbakonam when everything goes fine after COVID. So this is the mark list of the first degree of arts of University of Madras in 1907, where he appeared for, there are several mistakes. His name is written as Ramanujam, date of birth written as 1888, etc. So he has written 5 papers. In fact, he didn't write physiology and history, but he wrote English, Sanskrit, and mathematics. And in English and Sanskrit, he failed, but mathematics, he got only 85 out of 150. So mark doesn't show any strength of knowledge. And this is the University of Madras certificate given as a conduct and character certificate issued by the principal on 4th July 1905. Ramanujan was not promoted to the senior FA class and lost his scholarship. He joined Pachaipas College, Madras in 1906. Within 3 months, fell ill and returned to Kumbakonam. Appeared for the Madras University exam in 1907, but unfortunately again failed. And that came to an end of the formal education in India. There are several people who were helpful and mentors of Srinivasan Ramanujan in various stages of his life. To mention, V. Ramasamy Iyer, founder of the Indian Mathematical Society, then called Analytical Club, and editor of the Journal of Indian Mathematical Society. His teacher, professor at Kumbakonam, Professor P.V. Seshu Iyer, and then S. Narayana Iyer, treasurer of the Port Trust, and Sir Francis Spring, who was chairman of the Madras Port Trust, and Devan Bahadur Ramachandra Rao, though he was not a mathematician, he was an IAS officer, ICS officer, collector at Nellore, and obviously G.H. Hardy, Neville, and others. I have a special mention about P.V. Seshu Iyer because he also belongs to Palghat. I am also from Palghat of Kerala. So his village is called Perumbur. And I went back to this place and inquired about P.V. Seshu Iyer. Obviously, nobody was knowing him. I think after spending a few years in his home village, Perivembu, he went to Chennai or some other part of India. He became a professor at Kumbakonam. No traces of historical evidence could be found about Seshu Iyer in his home village in Kerala. This is Srimati Janagi, whom Ramanujan married in 1909. And please note that Ramanujan passed away in 1920 and Janaki Ammal passed away only in 1994. Therefore, as an Orthodox Brahmin, she had to be remained as a widow for about 74 years. And this is the famous letter that Janaki Ammal wrote to all those mathematicians in India and abroad who could help to, who could contribute for the sculpture in memory of her late husband, Mr. Srinivasa Ramanujan. What is more interesting is the caption of the letterpad says, as Janaki Ammal, wife of late Srinivasa Ramanujan, mathematical genius, written on 17/3/1984. So this is something surprising and interesting. So Janaki Ammal addresses Srinivasa Ramanujan as a mathematical genius. So this is the historic letter that Srinivasa Ramanujan wrote to Hardy on 16th January 1913. Among many results and formulas of mathematics, one striking formula that it was there is the most famous formula coming out of the Riemann zeta function, that 1 plus 2 plus 3 plus etc. is equal to -1/12. And that is, any schoolboy will say that it's a wrong result because 1 plus 2 plus 3 plus etc. is a divergent series. And not only that, it is a terms are positive, and you cannot expect a series whose positive terms having a negative value, and 1 plus 2 plus 3 plus etc. is -1/12. When Hardy saw this result in his first letter of Srinivasa Ramanujan, he was very much sure that Ramanujan is at least as competent as many other stalwarts and pioneers in mathematics who also made the same mistake like even Gauss. So the letter contained, among many things, this letter is very pathetic letter. I beg to introduce myself to you as a clerk in the accounts department of the Port Trust office at Madras on a salary of only 20 pounds per annum. That is 1,400 rupees possibly per year. And I am now about 23 years of age. After leaving school, I have been employing the spare time at my disposal to work at mathematics. And which is more pathetic is that to preserve my brains, I want food. And this is now my first consideration. I think in 2021, no mathematics student anywhere in the world or anywhere in India is going to write such a letter, because I think such students are taken care of, though not completely. As I said earlier, Ramanujan became Fellow of Royal Society London, the first Indian scientist, on January 24, 1918, recommended by Hardy and McMahon. In fact, day before yesterday, my good friend Ken Ono gave a talk in Cochin University National Mathematics Day lecture, and he mentioned about the original nomination form of Srinivasa Ramanujan for his FRS, kept by Krishnaswamy Alladi during the 100th year celebration of his nomination as FRS in 2018. And you should see the name of people. These are some names of the people who signed, who recommended Srinivasa Ramanujan for his FRS, included Hardy, Whitehead, McMahon, Forsyth, Alan Baker, Littlewood, and many, many others whom I could not read because of the lack of clarity. So this is the last letter to Hardy in 1919 on mock theta function, which is his area of specialization. And there are three people, as I mentioned, who are involved with the works of Srinivasa Ramanujan since many, many, many years, of which my good friend George Andrews, who had visited Cochin University in 1981, when I was a research student there, and I had the responsibility given by my guru, Professor Wasir Abdi, to take around George Andrews to various beautiful tourist spots of Cochin. So I had spent a lot of time with him, and we are still friends. And I will show you a preface that he gave to me for writing an article in Srinivasa Ramanujan. This is the photo of George Andrews, who visited Cochin in 1918. Who stands here is my guru, Professor Wasir Hasan Abdi, who made me whatever I have become is due to him. As I said, Ramanujan's books were lost in Trinity College libraries. So the manuscript in which Ramanujan recorded the mathematical discoveries of the last year, 1919 to 1920, is popularly now known as Lost Notebook. Its whereabouts were unknown until it was rediscovered by George Andrews in 1976 in a box of effects of G.N. Watson, stored at the Wren Library at Trinity College, Cambridge. So this is the point which I mentioned to you. I wrote an article on Srinivasa Ramanujan in 2015, an academic pilgrimage to Srinivasa Ramanujan's Kumbakonam. So I requested George Andrews to give a preface or an opening sentence, which he was kind enough to give me. The statement reads as follows. One of the most amazing and wonderful mathematicians of all time is Srinivasa Ramanujan. He provides a shining example for each of us in at least two important ways. First, his magical genius has provided mathematicians for the last 100 years with wonderful research directions that have greatly enriched our understanding of many areas of mathematics. Second, he has shown us that someone born in poverty, please underline, that someone born in poverty can achieve success beyond our wildest dreams. The world is a better place because he lived. George Andrews, the Pennsylvania State University. I think that is a great tribute by George to the great Srinivasa Ramanujan. Another person is University of Illinois Professor Bruce Berndt, who is of the same age of George Andrews. He has five-part series called Ramanujan's notebooks, which are all famous. And there is a comment made by Bruce Berndt on Ramanujan. All of us know that Ramanujan did not give a formal proof of any of his statements and theorems. So he followed literally the style of George Carr, who also was not keen on providing proofs. He was also usually writing in a slate carried over to notebooks only when it was a need, and that was also the final statements, because no money to buy white paper to write. And also he didn't feel that theorems needed proof, because that shows his sharp power of intuition. As you all know, Honorable Prime Minister Dr. Manmohan Singh declared the year of mathematics as 2012. There is a general perception in our society that the pursuit of mathematics does not lead to attractive career possibilities. This perception must change. So all of us have the responsibility of informing our younger generation that mathematics is worth doing. And this book of Robert Carnegie, Professor Dr. Manmohan Singh appealed to mathematical community that we should translate it to Indian languages. As far as I know, it has been translated to 7 Indian languages. And this is the Malayalam version published by Kerala Language Institute in collaboration with the Ramanujan Mathematical Society under the interest leadership of Professor M.S. Raghunathan, who was the president during 2012. So this was translated by Professor Ramachandra Menon, Professor T.M. Shankaran, and Dr. W. Crystal Flory, and I was fortunate enough to be the technical consultant. This is the Bangla and Kannada translations, and this is the Gujarati and Tamil translations. Tamil translation is by Professor Vanchinathan, and Gujarati translation by Professor Vaidya, and Kannada translation by C.S. Aravinda, and Bangla translation by Parthasarathi Mukhopadhyay. And Shastra University started giving Shastra Ramanujan Prize from 2005 onwards. And the first set of recipients included Manju Bhargava, who got a Fields Medal after that, and K.S. Soundararajan, who is now in Stanford. So this is a project, a very prestigious project of Ken Ono of Virginia University, USA, called spiritoframanujan.com. In order to honor the legacy of Srinivasa Ramanujan, the Spirit of Ramanujan STEM, Science, Technology, Engineering, and Mathematics Talent Initiative, supports emerging engineers, mathematicians, and scientists who lack traditional institutional support through financial grants and mentorship opportunities. Last day to apply for 2022 scholarship is 30th April. And I am very happy and proud to read out the names of 2017 awardees, which included a boy from Kerala, Trichur, Adit Vishnu, who was spotted by me because he got the first rank in the regional mathematical Olympiad 3 times, and he is currently a BS student in the Institute of Science. And Adit Vishnu visited several US universities 3 times consecutively till 2018, including Emory University, where Ken Ono was working. As I said, Ken Ono gave a National Mathematics Day lecture at CUSAT yesterday. So I strongly feel that not only Srinivasa Ramanujan, we should also celebrate great mathematician. And like I think this usually I give as a question to the students to identify these people. Of course, you will be definitely identifying them, but I'm not very sure whether you will be able to identify this lady, T.A. Saraswati Amma of Kerala, who did a lot of work on Hindu geometry. And in Kerala, in the Kerala Mathematical Association conferences, we have an endowment lecture, memorial lecture in the name of T.A. Saraswati Amma. So all these great mathematicians and scientists should be known to the younger generations of the country. Sujata, this is part 1 of my talk. I don't know whether I have time. If I have 5 minutes, I will tell only one point. Sujata, I have to give me a permission. Just 2-3 minutes.
Okay. Sorry, I was muted.
Okay.
Thank you very much.
just
Okay.
mention-
5 minutes more, please.
Yes, thank you.
Yeah.
I will discuss only one aspect of his work, As I said, I'm not competent to talk about his work in detail, but this is something interesting because of several reasons. Highly composite numbers, his article on which appeared in Proceedings of the London Mathematical Society from pages 347 to 409 in 1915, where he mentioned about the highly composite numbers, numbers which are such that the divisor function is greater for any smaller n. That is, the number of divisors of n is greater for any smaller n. And the first few are 1, 2, 4, 6, etc., which is found in the online encyclopedia of integer sequences of Sloan. And you will be knowing that infinitely many such numbers are there. Ramanujan in 1915, out of his memory, no computer, no WhatsApp, no mobiles. In 1915, he listed 102 highly composite numbers up to this number, but omitted this number in that list. And you will be surprised to know that this omission was noted by none other than T. Vijayaraghavan, who was also a student of G.H. Hardy in Oxford in 1920s. Thirukannapuram Vijayaraghavan is also a person which is not very much known, who is less known. We have to celebrate him also, who was living in 1902 to 1955. He was elected as a fellow of Indian Academy of Sciences in 1934. This is the handwriting of Srinivasa Ramanujan. SR listed 102 highly composite numbers, starting from 2, 3, 4, etc. This comes under the 2-volume book on notes of Lost Notebook of Ramanujan by Tata Institute of Fundamental Research. I think I need not explain why 24 is highly composite. Just 1 second. You know, number of divisors of 24 is 8, of which there are some of them are 1, 2, 3, 4, 6, 8, 12, 24. So if you look at all numbers, composite numbers up to 24, 23, 19, 17, they are all primes, so I need not check it. I need only worry about composite numbers. And if you look at all numbers, all composite numbers less than 24 will have number of devices less than that of 24, which is 8. So these are all things. This is the applications of Srinivasa Ramanujan's works in digital signal processing and filter banks, and also multiple signal classification. There was a celebration of the centenary of his selection as FRS London on October 1918, where so many people like George Andrews, Bruce Byrne, Peter Sarnak, Krishna, Alex Lobachowski, Sujata, and Vaidyanathan gave talks. There is a notion of Ramanujan graphs also, and as an optimal expanders, it's applied in post-quantum cryptography. His conjecture concerning the size of Fourier coefficients of modular forms, Selmer groups and group representations, string theory, black holes, moonshine effect, etc., are still pursued, which is a great surprise as far as many are concerned. So these are my personal collection of photos with George Andrews, Richard Oskey, and Ken Ono. This was taken a couple of years ago. And for further reading, there are several information that you get about Srinivasa Ramanujan, his life and works. I have just mentioned some of them. And this is a humble tribute to Srinivasa Ramanujan by writing an article last year in the leading Malayalam news magazine called Madhurabhumi. There are several other books. So I always these days conclude my talk with the call for breaking the chain as social commitment. And this is a small article which I wrote on Christmas and mathematics. And thank you very much for your patient hearing. And welcome to Kerala anytime after COVID-19, and wish you all a healthy 2022. Thank you.
Thank you very much,
Thank you, Professor.
Professor Vijay Kumar, and for the very inspiring talk on Ramanujan. He really took us, all of us, to Ramanujan very closely, and all aspects related to him we are so enthralled. And Professor Vijay
Thank
Kumar
you.
especially is very much part of our faculty of mathematics also. He has edited courses on graph theory as a graph theory expert, and many other contributions he has done. And I'm very thankful to him. He is for his inspiring lectures. And now I think we will have Professor R. Balasubramaniam. As I said, that he is a very well-known number theorist, and his works on number theory, and he is already National Award professorship winner also. And Sir I welcome you all, and I think we have fortunate to have one of his student, Dr. Venkatraman also, who also works in Ambacheri. So we are also fortunate to have his contributions also. And now I request Professor R. Balasubramanian sir.
Yeah.
Talk on circle method, and which is very legendary work of Ramanujan. I'm sure that he will inspire with his Ramanujan work.
Yeah.
Over to
Thank you for your invitation, but I still have not got the permission to share my screen.
Professor Deepika.
Yeah, I think you can share by the time, Madam, our Honorable Vice Chancellor, sir, has also joined. So,
Yeah, thank you, sir. Our Honorable Vice Chancellor, Professor Nageshwar Rao, sir, has joined, and we have, sir, we have just have one talk by Professor Vijay Kumar. He talked on the man who knew infinity, and now we are going to start. Shall I have your address, sir? Welcome, sir. Yeah. Let me just start. Professor Deepika?
yeah, I think he can share the rights.
I
as
don't
well.
see. I don't see
Please
the
share
time.
your screen. Maybe.
सर आप एक बार आप वो कर दीजिए सर.
Deepika, has the previous speaker stopped presenting?
Please
Yeah,
continue.
he has
And then
stopped.
again rejoined. I think that also
No.
would help.
Professor Vijay Kumar has stopped sharing. Now I think he can share his screen. There is no glitch in that.
I don't
That may be
see.
the reason that you couldn't share. Balu, you can log in again and then try to do that.
Yeah.
Oh, I see. Okay. Then I'll do that.
Hello, Venkatraman.
Ask now for his address. Okay, please.
Yeah, I think Dr. Venkatraman, who is a student of Professor Bala Subramanian, would like to introduce him. It's over to Dr. Venkatraman.
Sure. Can you hear me?
Yeah. we can.
Yes.
Yeah, okay. Professor Balasubramaniam finished his master's in Pundi Pushpam College, Tanjavur, and then he joined Tata Institute of Fundamental Research as a doctoral student. He joined as a student under Professor Ramachandra, who started in algebraic number theory. He solved a problem posed by Professor Ziegel. Then he moved on to transcendental number theory, and then to analytical number theory. So by the time Professor Balasubramaniam joined, he was working in analytical number theory. So Professor Balasubramaniam joined and started working in analytical number theory at the time. For his PhD work, he improved 20-year-old result due to Titchmarsh, which was supposed to be a breakthrough at that time. And he got a Young Scientist Award for his work, for his PhD work. Then later he spent an year in, after his PhD, he spent an year in Institute of Advanced Study, where he did path-breaking work that led to actually that ultimate solution of the value of Z4, small Z4, along with Professor Deschouye and Dress. And so he'll be telling you what little Z4 is all about, I'm sure, in his talk. Professor Balasubramaniam has collaborated with many mathematicians across the world. He has written papers with Professor Neil Koblitz, Professor Ram Murthy, Professor Kumar Murthy, and many others. He has worked not only in number theory, he has contributed to computer research in complex analysis, and he has also worked on graph algorithms with computer scientists. So he has a very wide repertoire of work. He was awarded Shanti Surba Bhatnagar Award, and later he was awarded Padma Shri also. So we are privileged to hear versatile mathematician and popularizer. His talks are really, he's a good speaker too. So I mean, I am sure you'll all enjoy this session.
Thank you, Dr. Venkat. Can I, Professor Balu?
So,
Balasubramaniam,
are you
are you
able
able to share the
share screen now? Please
ask
unmute
whether
your
he
mic. We cannot hear you.
Sir, please unmute.
I can unmute, but I cannot
Yeah.
share the screen. You can.
Okay. So can you just send it on our mail? I mean, Dr. Venkatraman, could you have that?
No. Actually, he is planning to use his Microsoft Surface. So he's planning to write on the this thing. What is the problem? Where are you not able to share? It's not allowing you to share, or what?
Yeah, but I don't see the thing called share the screen. There should be a.
No. What are you? There is a square with upward arrow. You just click on that, it will start sharing.
Oh,
At the
that's
bottom,
all.
there are icons. There is a
Yeah.
square with the upward arrow. Just click on that.
Okay. Now share your entire screen.
Yeah.
Okay.
Thank you.
Okay. Now I have to share. Okay.
You share entire screen, entire window.
Yeah. Now are you able to see?
No, you have not started it. You have to
You have not started.
No, I mean I did the upward arrow.
Yeah, just click on
Yeah,
that.
you click that, select that window.
Okay.
Just select that window and then
Or you
entire
can say,
screen.
Yeah.
Please, yeah,
Yeah.
it's visible now.
Yeah.
Now it's
Very
visible.
good, sir. Yeah. Thank you.
Yeah, but it's not visible for me. 1 minute. It's visible for you, but not visible for me.
Yeah. You just focus on the screen which you want to show to us because you are already logged into the meeting now, so we can
Yeah.
see and hear all the.
You click here to return. No, I mean.
You can go back by pressing Alt and Tab, 2 keys simultaneously. There would be many windows, so you can pick whichever window you want to select. Alt and Tab keys simultaneously if you want to switch to another window.
Wait. 1 minute, sorry. Exit full screen. Yes.
Balu, just click on this thing, a window, and select the window where you are going to present. Just go to the arrow thing again and select the window.
Select a window. 1 minute.
This one, yeah.
Okay.
Stop presenting. Just stop presenting.
Stop presenting. Okay.
Now click on the thing again.
Again. Okay. Now a window. I see.
Okay. And select the window you want to present. It will show you many choices. The one with where you want to write, you just select that.
Are you able to see it now?
Yeah, fine, sir.
Fine. Okay.
Fine.
Then I can start. Okay.
But you will need to scroll up and down, okay, Balu?
Yeah, that's no problem. Okay. Yeah.
Thank you.
Okay. Thank you. Thank you for this invitation. to talk about circle method. Are you able to listen to me?
Sure,
Yeah,
sir.
we are able to hear you, Balu.
Okay, fine. Okay. First of all, let us start with the origin of the circle method. For the origin of the circle method, let me quote from a book of G.H. Hardy. The title of the book is Ramanujan, 12 Lectures on Subject Suggested by His Life and Work by G.H. Hardy. I mean, he gave 12 lectures on the work of Ramanujan somewhere in 1930s. And that has been published as a book. And in fact, I would urge all of you to go through this book to see really what Ramanujan has done. And I should also probably say that some sort of a sequel to this book has been recently written by both Ramamurthy and Kumarmurthy. Okay, good. Now let's see what does the Ramanujan thing say. Ramanujan's letters to me, this is what Hardy says, Ramanujan's letters to me, which are reprinted in papers, contain the bare statements of about 120 theorems. That's all. I mean, as the previous speaker was explaining, Ramanujan was following the style of Carr, and Carr has given just the results. And in fact, the Carr's book was really supposed to be for people who were preparing themselves for the competitive examination, not for any mathematical examination. And therefore, before going through the competitive examination, you would like to see all the formula which you have forgotten. And that's all what the Carr's book is supposed to be. But since Ramanujan learned his mathematics from Carr, he more or less followed the same style. And of course, Hardy in his book doesn't quote all 20, even though they are available. And I quote 15. Therefore, 15 of the theorems is what he quotes. And they include two theorems, 1.14 and 1.15. This 1.14 is what is very important for us. I will talk a little more on that, which are as interesting as any. But they are very interesting theorems, except for the fact one of which is false and the other, as stated, is misleading. Okay, and the false theorem is what we are interested. And the theorem says that the coefficient of x power n in 1 minus 2x plus 2x power 4 minus 2x power 9 plus 2x power 16 minus etc. That's a power series. You see the coefficients alternate. The first coefficient is 1. All the remaining coefficients are 2, but alternatively minus 2 plus 2 minus 2 plus 2, etc. This is what is called a power series. And that power series, as all of you would have known, is convergent in mod x less than 1. And mod x equal to 1, it won't be convergent, it will be only conditionally convergent. And take this power series with mod x less than 1 and take the inverse of that. And then what is the coefficient of x power n in the inverse of this power series? And Ramanujan claims that that number is the integer which is nearest to 1 over 4n into cosine hyperbolic pi root n minus sine hyperbolic pi root n divided by pi root n. Okay, the point is I will talk a little more about this particular expression 1 minus 2x plus 2x power 4, etc. and the inverse, and explain why this coefficient is interesting. But what is wrong in it? What is wrong in it is the function in 1.14 is a genuine approximation to the coefficient. That's the most important point. And this formula was not known before the Srinivasa-Ramanujan things. I mean, it's not only people didn't know how to prove it, people even did not know what exactly to expect. What should be the formula that you should be expecting for the coefficient x power n? But not as so close as Ramanujan imagined. Ramanujan imagined that this difference will be bounded, but that is not true. This is the first main term, and then there's a second main term, third main term, etc., etc. And it's not really bounded, the difference is not bounded. But that was a mistake. But the first main term, which is the most interesting aspect, is really true. And Ramanujan's false statement was one of the most fruitful he ever made. For people to say that he made a false statement, and that was fantastic. I mean, nobody would appreciate a false statement. But this false, as I told you, only in the sense that the error between the coefficient of x power n and that expression is not bounded as Ramanujan was thinking, but on the other hand, that expression is a very good approximation, and that was a great result. And since it ended up by leading us to all our joint work on partitions. Okay, therefore let's see. First of all, let's see what is it Ramanujan was trying to do. You take theta q equal to summation q power n square, which is what we had earlier, and I am going ignoring the minus 1 power n for convenience. And you see, when you look at the summation q power n square, the term corresponding to n equal to 0 will give you a coefficient 1. But the term n equal to 1 and minus 1, both are same. Q power n square, the value for q power n square, whether you take n equal to 1 or n equal to minus 1 are the same, and therefore that will give you a 2. And similarly, when n equal to 2 and n equal to minus 2 will give you the q power 4, and the coefficient will be 2, and so on and so forth. Therefore, if we ignore the minus 1 power n for a minute, then it is actually this q power n square is precisely what Ramanujan was looking at. 1 plus 2 times q plus 2 times q power 4 plus 2 times q power 9 and so on. And this is what Ramanujan was working in, and that is exactly this. And this is known to be a modular form of weight half for the group gamma naught 4 when q goes to e power pi z. And these are things which probably I would not be able to explain. I mean, they are all technical words. Let's forget it. And what this theta function is a very, very important function in number theory, in geometry, in physics, and every subject. And this theta function, and how does theta function inverse looks like is also an equally important question. And that's what exactly Ramanujan was interested. It is called the Jacobi's theta function. Since it's a modular form, it satisfies a transformation formula, which is something which again it will be difficult for me to explain. And but on the other hand, I will explain the transformation formula a little later in a different context. And Hardy realized that this method should be applicable for any function which has a transformation formula, in particular for partition function, which is precisely what Hardy was interested at that time. Hardy was interested in partition function, and then he was trying to see what is how one can do something on partition function. Let me define what is partition function. Partition function, I think, was defined in the previous lecture, but even then, let me again do that. The partition function Pn is by definition the number of distinct ways of representing n as a sum of positive integers. You take an n and try to write as a sum of positive integers, and with no repetition, the things can repeat, but you don't write 3 plus 2 as well as 2 plus 3. You write only one of them. You don't write 4 plus 1 and 1 plus 4. And if you do that, then how many ways the n can be written as sum of integers? For example, the value of the partition function at 5 is exactly 7, because 5 can be written as sum of integers in 7 ways. What are the ways? 5 can be written as 5. It can be written as 4 plus 1. It can be written as 3 plus 2. You see, I am writing in the decreasing order so that I will not be writing both 3 plus 2 and 2 plus 3. Therefore, by deciding to write in the decreasing order, then you are assured that you will not be repeating the same. And 3, it can be written as 3 plus 1 plus 1, 2 plus 2 plus 1, 2 plus 1 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1. Therefore, the 5 can be written in 7 different ways, and therefore one says that this partition function, the value of the partition function P at 5 equal to 7. Now, it so surprisingly happens that this partition function rather grows rather rapidly. What does it mean? For example, P200 is a very big number, which is 3, 9, blah, blah, and it's an 8-digit number. And therefore, P200 itself is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13-digit number, 3, 9, 1, 2, etc. A 13-digit number. Therefore, 200 itself can be written as sum of integers in these many ways. And what the question which Hardy was interested is that whether one can get again a main term for the partition function. Therefore, if you are given a large n, can you approximately say what would be the value of Pn. And it so happens that this Pn also has a transformation formula, and therefore it can be used, Ramanujan's method can be used, and therefore let's look at what the transformation formula is. The generating function for Pn, which is normally when you have some coefficients an, and if you want to study the coefficients an, one of the way is to really write the power series sigma an q power n, and then study the properties of the power series an q power n, and then that will give you some information on the coefficients an. And simple, this is precisely what we are going to do. We take the power series summation Pn q power n, and this power series is known to be equal to the product k equal to 1 to infinity 1 minus q power k inverse. And this formula is due to Euler. And in fact, Euler was the first one to write really the partition function and studied many properties of the partition function. And this product 1 over q power k without the inverse also has been evaluated. And this is also looks to be L equal to minus infinity to plus infinity minus 1 power L q power L into 3L minus 1 divided by 2. You see, first of all, you would be slightly wondering that the left-hand side is likely to have only positive powers because I am taking product q k equal to 1 to infinity. And how come this summation is from minus infinity to plus infinity? And really what happens essentially is that when L is positive or L is negative, in both cases, the exponent L into 3L minus 1 over 2 is positive. If L is positive, then L into 3L minus 1 over 2 is positive. If L is negative, even then L into 3L minus 1 by 2 is positive. And therefore, this is there's no problem there. Okay. Now the question is, what is the transformation formula? We said that this has a transformation formula. And what is the transformation formula? Remember, summation Pn q power n equal to product k equal to 1 to infinity 1 minus q power k inverse. And suppose I don't, this is one function in which Ramanuja was very interested. But instead of the power minus 1, suppose you write 24. That is also another function in which Ramanuja was very interested. That is, therefore, you are looking at a product k equal to 1 to infinity 1 minus q power k power 24 is what you are looking at. Of course, you are multiplying it by q. And therefore, let's write that function. Therefore, delta of z equal to q into product 1 minus q power k power 24. Of course, now you will be wondering why I write a z in the left hand side and q in the right hand side. What is the connection? And this q is equal to e power 2 pi I z. Therefore, if I write as q, then of course it gives you a power series. And instead of q, if I write e power 2 pi I z, then it gives you a Fourier series. Okay, therefore take this power series. Therefore, this power 24 also something in which Ramanuja was very interested. And write the coefficients of this power series as tau n. Okay, and this tau n is called a Ramanujan's tau function. And this delta z is called a Ramanujan's delta function. And Ramanuja had many conjectures on the tau n, etc. But that's for a different day. Now we are only looking at circle methods, which therefore whatever the work which is done on tau n, I will probably explain in a different day. But now this delta z happens to be a cusp form of weight 12 for the full modular group. Now, of course, I am not going to define what a cusp form, etc., etc. But on the other hand, I will tell you what this means. This means delta z is holomorphic in the upper of plane. Therefore, in other words, if you write q is equal to e power 2 pi z, and then you look at that, and that would not be even convergent in the negative of plane. Only the upper of plane, which means the complex numbers x plus iy, where the imaginary part of y is positive. That is what its upper of plane means. And this is x plus iy, where the imaginary part is positive, which means that as you can visualize, when you draw it, that will be the upper of plane. And delta z is a holomorphic in the upper of plane. And also the value at I infinity equal to 0. And that is exactly what the word cusp means. Cusp means that the value at I infinity is 0. And now you see, it's a weight 12 cusp form for the full modular group. That statement means, so this one can I hide? Yeah, good. Oh, that's nice. That statement means delta of AZ plus B by CZ plus D equal to CZ plus D power 12 times delta of Z. Therefore, there is a transformation formula which connects AZ plus B by CZ plus D to the value at Z. That is exactly what is called a transformation formula. And this, of course, is not true for all ABCD, but true at least for integers ABCD with AD minus BC equal to 1. And this form a 2 into 2 matrices and called SL2Z. And therefore, for all SL2Z, it is delta of AZ plus B by CZ plus D equal to CZ plus D power delta Z. This is the transformation formula. And once already realized that Ramanujan's formula can really use for everything which has a transformation formula, he used that, and Hardy Ramanujan proved that the asymptotic formula, which is a partition function, is around 1 over 4 n times the square root of 3 into exponential pi into square root of 2n by 3. I mean, this is a formula which is used everywhere, and you know exactly how Pn grows. Pn grows not exactly like an exponential function, but more like an exponential square root n function. Okay, that's how the Pn goes. And this is a consequence of circle method, okay, which they developed. And I would probably say a little more about the circle method, not with respect to these two problems, but to a different problem. And this problem is what is called a Walling's problem. Now, let me explain what the Walling's problem means, for which the circle method has been found useful. Lagrange proved that every integer can be written as sum of 4 squares. Therefore, you take however big a number you take, you don't need more than 4 squares. Whichever bigger number you take, and if you try to write n as sum of squares, just you can manage with 4 numbers. And now the question which Walling asks is it true only for power 2 or even true for power 3, power 4, power 5, etc.? More precisely, given an integer k, does there exist an S such that every integer can be written as sum of S kth powers, x1 power k plus x2 power k plus etc. xs power k? The minimum such S is called gk. Therefore, gk is the minimum value if it exists. Because it's not even clear whether that should exist at all. If I take the 7th power, for example, is it probably true that every number can be written as sum of 7th powers in a finite? I mean, some numbers may need a lot of them, and it may even need infinity, and therefore that will be the problem, because I need it for every n. Okay, first of all, let's guess how many will we need at all for any kth power. How many s? What will be the value of gk? What will we guess? Okay, for k equal to 2 and n equal to 7, we need at least 4 squares, because the 7 cannot be written as sum of 3 squares. When you try to write 7 as sum of squares, it cannot be, you need 4 squares. You can write only as 4 plus 1 plus 1 plus 1. Okay, therefore you cannot do much better than that. There is no way you can write it as sum of 3 squares. And if you think for a minute why it happens, once particularly when the number is small, then you do not have many squares to play with. If the number is something like an n, then you have a 1 square and 2 square. That's all. You can't even use 3 square. 3 square is 9, already is bigger than 7. Therefore, you have only 2 squares, 1 square and 2 square. And that gives you the really problem. And therefore, you need 4 squares. More generally, we can try to do the same thing. Let m be the greatest number less than 3 power k and a multiple of 2 power k. Choose a number which is less than 3 power k and a multiple of 2 power k, and choose that n equal to m minus 1. Since m is less than 3 power k, n is also less than 3 power k. And once n is also less than 3 power k, then you have a problem. You have only 1 power k and 2 power k to play with. And therefore, whatever you are trying to do, you have to do with only 1 power k and 2 power k. Let's say a few examples. K equal to 3. K equal to 3, I want to choose that number m, which is less than 3 power 3, but also a multiple of 2 power 3. A number which is less than 3 power 3 and a multiple of 2 power 3, and the biggest number like that means 24. And therefore, m is 24. and that means n is 23. And now when you try to write the 23 as cubes, you have only 2 cubes and 1 cube to play with. You can't even use 3 cube because 3 cube is 27, which is bigger than n. And therefore, when you play with 2 cube and 1 cube, then you end up with 2 cube plus 2 cube plus 1 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 cube. And therefore, you need 9 cubes. You cannot manage with the 8 cubes at all. Therefore, G3 has to be at least 9. And the same thing you can try for k equal to 4. And then you have to look at the number which is less than 3 power 4 and a multiple of 2 power 4 and the biggest number like that. And that number is 80 and n is 79. And then you try to write 79, then you need at least 19 fourth powers. You can use this argument, and generally when you do it for kth powers, you will end up saying that g power k is at least 2 power k plus integral part of 3 by 2 power k minus 2. The integral part means if it is 7.3, you take it as 7. If it is 14.29, then you take it as 14. Is a number which is the biggest integer, which is just smaller than that. Now, variance conjecture, which is not a correct statement, but anyway, Rayleigh conjecture that the equality holds. Gk equal to 2 power k plus 3 by 2 power k minus 2. And in fact, Rayleigh did not really conjecture. Rayleigh conjectured that Gk exists, that's all. That means Gk is finite. That's all Rayleigh conjectured. It was Hardy, more or less, who made this conjecture, Gk equal to 2 power k plus 3 by 2 power k minus 1. But the question of Gk exists was first proved by Hilbert, okay, and which is not by circle method. That's by a completely different method. And now circle method has been used to do something for this problem. Okay, what is the thing? In this case, you look at the generating function. The generating function is summation m equal to 0 to infinity q power m power k. That's a generating function because you are only looking at the powers of k, and therefore q power m power k, the generating function. This unfortunately has no transformation formula. Therefore, whatever that Ramanujan did at the first sight, you would think probably this method cannot be applied because it has no transformation formula. However, Hardy and Littlewood observed that the same circle method can be applied in this case also. Even though it does not have a transformation formula, still they can apply the circle method. And this method was further refined by Yuval Miller, Harold Davenport, and others. And the others, I will talk a little more about some others little later. Okay, therefore now let me just explain in this context what is circle method. Okay, this is not exactly what Ramanujan was having in mind because the way I am going to explain, there will be no circle at all. But on the other hand, this is what circle method gives. We want to write a number capital N as a sum of s kth powers. We want to know whether this capital N can be written as sum of s kth powers. And let's define f of alpha equal to summation e power 2 pi I alpha m power k with m less than or equal to n power 1 over k. Remember, this is the same generating series which you wrote, summation q power m power k, with the except that the q I have replaced by e power 2 pi I alpha. Okay, therefore let f alpha equal to summation m up to n power 1 over k e power 2 pi I alpha m power k. Take f alpha power s, which is e power 2 pi I alpha m1 power k plus m2 power k, etc. ms power k, the summation over m1, m2, etc. ms, and which can be now written as summation over rn e power 2 pi I alpha.
Professor Balasubramaniam sir,
Yes.
Excuse me for 5 minutes. Our Honorable Vice Chancellor has joined us.
Okay, sure.
Yeah. So I'll just ask him to, sir, can we have the presidential address after his talk? Or I welcome you, sir, for this event of National Mathematics Day. And we are really honored that you have joined us for.
I'm already here. I am already here. Please continue. Please.
Yeah. So can I have that? We can have your presidential sir after Professor Balasubramaniam.
Please.
Okay. Thank you. Thank you very much, sir.
Okay, sir. Thank you.
Please, Professor Balasubramaniam, sir. I'm sorry. Please continue.
No problem.
Yeah, that was really interesting. Yeah.
Yeah. Okay. Therefore, if we write f alpha power s, is equal to e power summation e power 2 pi a alpha m1 power k plus etc. ms power k. And this can also be written as summation Rn e power 2 pi a alpha n, where Rn is the number of ways of writing n as m1 power k plus m2 power k etc. ms power k, where every mi is less than n power 1 over k. Now the question is, therefore, since Rn is a number of ways of writing n as m1 power k plus etc. ms power k, if I want to know whether the capital N can be written as m1 power k plus m2 power k etc. ms power k, then this is equal to asking whether R of capital N is positive, because R of n is the number of ways of writing it. And if you say that the number of ways of writing capital N as m1 power k plus m2 power k plus ms power k, that number is positive, that means at least in one way you can write it. Therefore, essentially what we are interested in proving is that Rn is positive. But unfortunately, we do not know how to prove that something is positive unless we know roughly the order of the element. And that's exactly what the circle method originally conceived by Ramanujan said. That you take this Rn, and if we would like to know the rough value of Rn, the approximate value of Rn. And that is precisely what he did for the reciprocal of the theta function. For the reciprocal of theta function, he wrote the coefficient of x power n, a first approximation to it. And that is precisely what they did for the partition function. And that's exactly what we will do in the variance problem also. We will write an asymptotic formula for this Rn. And once you got an asymptotic formula, then from that we will deduce that Rn is positive. From that we will deduce that this capital N can be written as sum of s kth powers. Now, how do you get the Rn? That will be trivial, because you can just use the Fourier inverse, and the Fourier inverse will give you 0 to 1 f alpha power s e power minus 2 pi a n alpha d alpha. Now, I have not explained the partition function case, but what I have meant is analogous to the partition function case. One can expect that the main contribution to the integral comes from a small neighborhood of alpha equal to a over q for some q less than or equal to q. Therefore, you take rational numbers with the small denominators and take a small neighborhood of such rational numbers. Then the rational numbers, the small denominators and the neighborhood of that numbers, that will contribute mainly to the integral. And the rest, which we don't have much of a control, probably will not contribute much to the integral. Therefore, we write 0 to 1 as capital M union little m, where capital M, which is called the major R, is those alpha which are in the neighborhood of a over q for some small denominator q less than or equal to q, and the rest is minor R. And in the capital M, of course, since we know the value at alpha and therefore the value at the neighborhood, we can actually get an asymptotic formula for fs, and then you can actually integrate explicitly, and then this integral is of the order n power s over k minus 1. Therefore, that is the main contribution, n power s over k minus 1. And this part is easy, almost more or less a high school exercise. But the main difficulty comes in proving that the minor R contribution is in fact small. It is of the smaller order. Anyway, using this idea, and now I want to say a little more, and this is one problem in which the Indian contribution has been very much, lot of Indian contributions for that. And for example, using these ideas, and of course the ideas which were developed by Vinogalav, the Indian mathematician S.S. Pillai was able to prove almost the conjecture. He proved that the value of Gk is exactly what, as already guessed, 2 power k plus 3 by 2 power k minus 2, or probably sometimes one more, 2 power k plus 3 by 2 power k minus 1. This was proved by Pillai. And of course, some small values were already known, but then he proved it for every k. In particular, G3 was already known to be 9, that is due to Beveridge and Kempener. And G4 was known later. That was the only last one which was to be decided. That was done by Desue at 1986. And G5 was done 37 by 1964, and G6 is 73, Pillai, and so on and so forth. And therefore, Pillai proved a great result that the value of Gk is exactly what already guessed, or probably sometimes one more, but it is even expected that this one more will never happen. It is exactly as hardly expected. But on the other hand, that whether this is as hardly expected or one more cannot be decided by circle method. It comes in a completely different ideas. This is called the Ross theorem, or the approximation of algebraic numbers by rational numbers, etc., which is a different question. Now, an equally interesting problem is capital GK. Okay, what is capital GK? And now we said that the little GK is more or less decided by those numbers which are less than 3k, which is a multiple of 2 power k, because you have 1 power k and 2 power k only to play with, and you don't have many kth powers to play with. Suppose we ignore such numbers, and therefore you are looking at only those n's which are rather very large. If it is very large, then you would expect the value of s to go down considerably, because the small numbers will not play a role at all. And that is called GK. Therefore, every large integer is a sum of s kth powers. This is called capital GK. Even though the value of little GK is known for all k, because not only Pillai proved that this is either the Hardy's value or Hardy's value plus 1, he also even gave a criterion to decide which one of those two. And therefore, given a k, I can always know what is the value of GK. But it will be either the Hardy's value or Hardy's value plus 1, but that's a criterion given by Pillai to essentially decide. And in fact, there are other Indian mathematicians like Raghubunde and others who are also instrumental in making that criterion well. But in the case of capital GK, the value of capital GK is known only for two values, namely k equal to 2 and k equal to 4. For k equal to 2, it is due to Lagrange, and k equal to 4, it is due to Davenport. And the capital GK is known only for two values. Now I said about the Indian mathematicians, a similar question can be raised for integers in a number field. You take a number field and then you ask the same question of the GK, and let me not explain much on that. But on the other hand, I should say that C.P. Ramanujan has some remarkable results there, great results there. There is another problem which is used where the circle method has been useful, and that is what is called the Goldbach's conjecture. And what is Goldbach's conjecture? In 1742, Goldbach raised some conjectures in a letter to Euler. And the first conjecture is that if you take an even integer 2n, whether it can be written as sum of 2 primes. The conjecture is every even integer can be written as sum of 2 prime numbers. And one more result also he wrote, every integer can be written as sum of 3 prime numbers. Every n can be written as sum of p1 plus p2 plus p3. And circle method has successfully used to solve this problem. For example, regarding a, whether every even number is a sum of 2 prime numbers, we know the theorem due to Chen, which says that every even number is either the sum of 2 prime numbers, p1 plus p2, or p1 plus a product of 2 prime numbers. Either p1 plus p2, sum of 2 prime numbers, or a prime plus a product of 2 primes. And also we know that there exists a positive constant such that the number of exception to the conjecture is O of x power 1 minus c, which is due to Montgomery and Vaughan, which means that the exceptions are very less. Practically, the conjecture A is true for practically all the elements. If at all there are exceptions, the exceptions are very rare. Regarding B, Gerard Helfgott announced that the ternary Goldbach's conjecture is true. And this proof runs for around 160 pages with a lot of calculations, and I don't think it has been published yet, but it is still available. And we know, therefore, the conjecture is true that every integer can be written as sum of 3 prime numbers. And now we come to the last slide, which is very interesting. Surprisingly, there's a combinatorial problem to which Roth applied the circle method. I mean, circle method, so far you are trying to see that whether the n can be written as sum of 2 prime numbers, n can be written as sum of kth powers, only type of questions. But Roth used it for a combinatorial problem. What is a combinatorial problem? Let A be the subset of 1 to n integers. Let A be a subset of 1 to n. And if A is large, one would expect that A contains a 3-term arithmetic progression, A plus D, A plus 2D. And Roth showed if there exists a positive delta, and if n is large, and the cardinality of A is bigger than delta times n, which means that the density of A is positive, then A definitely contains a three-term arithmetic progression. That's all. You just need a positive. Cardinality of A by cardinality of n should be strictly zero, bigger than 0. Bigger than, therefore, the cardinality of A should be delta n. And in fact, he showed that if it does not have a three-term arithmetic progression, then B has only O of n over log elements. And in fact, summarily extended it for any k. That if A cardinality of A is bigger than delta of n, A contains a k-term arithmetic progression, but that is not by circle method, that's by combinatorial method. But now various other proofs due to Furstenberg and Gowers and others using other ideas, ergodic ideas, are also known. Therefore, we see that the circle method has been very powerful, and even though Ramanujan's original letter talks about the inverse of the theta function, it has been applied to various other problems, including partition function, including Variance problem, including Goldwasser conjecture, and you can actually combine both Waring-Goldwasser conjecture and even combinatorial problems, and turned out to be one of the very, very powerful tool in number theory. And with that, I will stop. Thank you.
Thank you so much, sir, for enlightening with the circle method. I think we can have the discussion on this after a little while. Honorable Vice Chancellor has joined.
Yeah.
So can I have his presidential address? Then we can have the discussions on this circle method and
Deepika, please stop. Ask him to stop presenting.
Professor Balasubramaniam, may I request you to please stop sharing the screen?
Yeah.
Yeah. Now, thank you, Professor Balasubramaniam, for explaining Ramanujan's work on partition function and circle method in detail and apprising us of the further contribution and application in the area. Now, I request our director to invite Honorable Vice Chancellor, sir.
Sir, Honorable Vice Chancellor, sir, thank you very much for honoring our National Mathematics Day event, sir. So we have two inspiring lectures, one by Professor A. Vijay Kumar. He talked on Ramanujan, the man who knew infinity, and Professor R. Balasubramaniam, he talked the most powerful method, circular method on Sri Ramanujan. Now, may I request you to, sir, give your address, sir? Sir? Yeah.
Good noon to all of you. First of all, I congratulate all of you, including me, on this great occasion, historic occasion, on which the great Indian mathematician Srinivas Ramanujan, he was born 134 years back. This is the 134th birth anniversary, and this we celebrate as the National Mathematics Day. I could not join in the first half an hour, but thereafter I was there. Of course, I have not used my video. I was listening carefully to Professor A. Vijay Kumar and Professor R. Balasubramaniam, both very difficult to understand mathematics. Now I start realizing about it and how a professor of mathematics, they contribute significantly to our learners. But I was a student also of mathematics. Only I can claim that at that point of time, we used to study mathematics only up to the class 10th compulsory. Thereafter, I have also studied mathematics for the ICMA examination. There, the high standard, that is calculus, etc., that was also being covered over there. And I have also cleared those things, but that is again a long old memory. Thereafter, I only look at Sujata ji or Deepika ji, the great scholars in the field of mathematics. And today I'm fortunate enough
Thank you.
to meet Professor A. Vijay Kumar ji and also Bala Subramaniam ji. When A. Vijay Kumar ji was talking, he was just referring the numbers which Ramanujam has used it. The PPTs were very, very clear, but for me, it is very difficult to understand. But even then, the way they tried to present before all of us, because I have seen that most of the faculty from science, even the School of Health Sciences, some regional centers, they all are attending it. It means that the people at large, they can understand the importance of this National Mathematics Day. I do remember that there was a circular from UGC also, which says that you must observe, you must celebrate this National Mathematics Day. But before that process has been initiated, Director School of Sciences, fortunately, she is also a professor of mathematics. So that is an added advantage. And she initiated the proposal, and today we could get the benefit of the expertise of Professor Vijay Kumar ji and Bala Subramanian ji. Both are sound in their subjects. And till this point of time, I was just thinking that mathematics is an exact science only. But now I could look at these researches, and thereby I started understanding that it is also analytical. It is also applied. And it can also be used as a science for future. So there are so many applications, and those applications, they give us a lot of room to think about the future. I do remember that there was Indian Statistical Institute also, and still it is there. Then statistics, it has emerged out of this mathematics. Still there are schools, there are departments where the mathematics and the statistics both are being integrated. And initially I do remember that the professors of mathematics, they nurtured this school of statistics. And later on, this school of statistics has also come up. Fortunately, in our school, we have got these two disciplines separately. And we are having very, very senior professors who have done a lot of work in that field. They are working in that. The actuarial science, it is the result of this. Even the computer science, the basics of the computers, even the physics also, we see that they all are closely related to this subject of mathematics. But out of these, all these subjects, when we see to it, we find that mathematics is much more exact than we see all these related disciplines. But for everyone, even in other disciplines also, like as a student of management, I do feel that mathematics is also a subject which is being taught to the students of management. It is being considered as a core course. And then in the second semester, the people, they talk about the operations research. So again, we see that if you want to become an effective manager, then also the understanding of the mathematics, the understanding of the operations research, and even the basics of statistics, they are very, very important. Because we have to look at the future. Look at any discipline, and there you find that mathematics is the base. I do remember when a student of class 1 also, they start telling the young learners, after ABCD, they talk about 1, 2, 3, 4. So that is the importance of mathematics. So after alphabets, or even before the alphabets also, the numbers are very, very important. All our mark sheets, they depict the number. Our divisions, they're also being depicted. Even NAC accreditation is also being given through numbers. So wherever we see that the numbers, they have got an important place. And these mathematics, they have given us the numbers. And we are fortunate enough to have Ramanujam, who was born in our country, to have our prestige all over the globe, saying that this numbers, it has come out from our country. And the light which we got from this is Ramanujamji. Remembering him, it's a great tribute to him also. and for us also, the importance of this particular discipline, which is quite useful to all of us. I must appreciate the school, because if I speak more, then people, they start seeing my own understanding, and then they start testing me about my mathematics. And then I will get, I think, relatively the marks which you can't imagine, the zero which was developed by the Ramanujan, that may come to me. So, but I am happy to see the two lectures which were delivered today, and the people who are trying to understand the research analysis which these two distinguished professors they have presented before us. They are quite useful to us. I wish all the best, and I'm thankful to both Professor Vijay Kumarji and Professor R. Balasubramanianji, who have spared their valuable time for us and helped us and guided us for our future endeavors. Thank you very much. Thank you.
Thank you very much, sir. You are always encouraging and guiding us for all these activities. And as you have already pointed out, the importance of mathematics more distinctly now. Usually mathematics is called the queen of science. Now I think it is king also, sir. You have already pointed not only beauty, and it is everywhere used. And I think that is when our purpose is also to popularize Ramanujan works, and Professor Balasubramanian has very simple way. This is such a powerful method, it's very difficult, but still he has tried all his effort to explain it in a very simple way. And as Professor Vice Chancellor sir has pointed out, we had mathematics department only at the first place, and we are really fortunate, rich to have now statistics department and other departments joined together as, and mathematics is part of that interdisciplinary as NEP is concerned. It is everywhere in the study of all other schools also, and we will definitely help all other disciplines enrich with mathematics. And as sir always pointed out, that we all put all these lectures and our talks in website also, so the students can always access that. So when that is one thing, and our students are also watch this YouTube live. We have very good number of learners, and I'm sure that I think our school has able to contribute and popularize this Ramanujan this thing, and I'm very thankful to you, sir, for your inspiring this thing. So now, can I have any questions or interaction with this thing for the audience with the Professor Balasubramanian? Yeah, Professor Vijay Kumar. Any? Thank you very much, sir.
Yeah, thank you.
Thank you. Any questions, please? Any?
Yeah, Professor Sinclair would like to ask to discuss something.
Yeah. Professor Sinclair, please.
Just a comment about the situation, Balu and Vijay. You see, we keep saying Indian mathematician and so on, and we did even for Harish Chandra and whatever. The point is, would their work have would they have seen more than what they were doing if they hadn't managed to get abroad and get the recognition and the contacts? And the work is done there. They are nurtured there. These are not Indians. The work is actually British.
Who?
Raman,
You don't understand. Sorry, can you repeat?
what I'm saying is, we say, Ramanujan, Indian and so on. He was born in India. But the mathematics would not have come if he hadn't got the support and the nurturance that he got in the UK.
That's probably true, but all that's exactly what they wanted to say.
So mathematics is this is, like I said, I would give credit to the UK for this mathematics.
That is probably true. I mean, unless there had been somebody like G.H. Hardy to nurture him, probably he would not have blossomed to this level. But in spite of that, what I wanted to point out was that this circle method, which is a powerful method, was already in his first letter to Hardy. Therefore, you cannot say that the idea came when he reached England. The idea was that in his first letter to Hardy, he wrote the formula for the inverse of theta function.
No, I'm not saying that he didn't have thoughts. I'd say all this would have been buried and gone.
That is true. That is probably true. I mean, there was not enough encouragement for him in India. That is true.
Therefore, I would give credit to those there. Actually, this is true for Harish Chandra, this is true for others, till recent times.
Yeah.
Very recent times. Even now, there's this problem, but not so bad as it was even 15, 20 years ago.
I completely agree with you. I mean, that the situation is much, much better now, but it was not so earlier. I mean, unless you had an encouragement, a pat from the back from the foreigners, then they were not really appreciated in India. That's probably true. Yeah, I would agree with that.
Madam, if you permit, I would just
Yeah,
like to ask
please.
something. Thanks to both the speakers. Though I'm not mathematician, I really enjoyed it. And Vijay Kumar sir, I have one small suggestion. After listening to you, I was feeling I was traveling along the life of Ramanujam. Why not make a small science movie which can inspire people? Like
Movie has already come. There have been at least
Yeah.
on life of Ramanujam.
a couple of Tamil movies are
Okay.
there. And I think this the DST things, what is this, Vigyan Bharati or something like that, they have also...
I think Vigyan Prasad.
Prasad,
Vigyan Prasad
had
has done.
this
They have some
Ramanujan
drama.
Yatra for 1 week show.
Yes.
So they had
A very nice movie.
Ramanujan Yatra last year. It was a 1 week program, and all the recordings are there on YouTube.
Thank you.
Thank you. Vijay Kumar has anything to add to that?
No, thank you.
Yeah. Okay. Yeah. Any other?
So with this, I
Balu,
think
what is the contribution of Trevor Woolley? Captain G? What is,
On Capital GK.
okay.
Capital GK, he improved a concept too, which is one of the fantastic achievement. Compared to
Anything latest done? Has there been either development in wiring method after Trevor Woolley important
Exactly.
development?
I mean, because instead of summing over all integers, he was summing over a special set of integers, and that gave him a great development. It was one of the great results.
So what is the status of Capital G now? We still know only for 2 and 4, is it?
Value is not only, I mean, the bounds have been improved tremendously by Vaughan and Trevor Woolley and others, but the value is still only known for 2 and 4.
Okay, Capital G. Okay.
Yeah.
Thank you, sir.
thank you.
Thank you.
So I think now,
Yeah.
yeah,
And also, I add to that, Professor Balasubramaniam has contributed this school also. He was our school board member also, and he had given valuable suggestion to the development of the school activities. I am very thankful to him, especially also. And now I think I request Professor Deepika.
So we are at the end of the program. I now request Dr. Vishal Varpa, member of Seminar and Cultural Committee, School of Sciences, to propose a formal vote of thanks. Dr.
Thank
Vishal,
you.
it's over to you. Yeah.
Thank you, Professor Deepika. Good afternoon, our esteemed, distinguished speakers present with us today on this grand occasion. Emeritus Professor A. Vijay Kumar sir and Professor Ramachandran Balasubramaniam sir, Honorable Chairperson Professor Nageshwar Rao sir, Vice Chancellor IGNOU, respected Director Professor Sujata Burma Madam, School of Sciences IGNOU, and all our esteemed dignitaries and colleagues. It is such an honor for me to get the opportunity to propose vote of thanks to you all dignitaries present in this webinar on the 134th birth anniversary of great Indian mathematician Srinivasa Ramanujan sir on the eve of National Mathematics Day. On behalf of the School of Sciences, IGNOU, we feel proud to extend a warm welcome to all the dignitaries attending this online webinar. We would like to express our deep sense of gratitude to both the esteemed distinguished speakers, Emeritus Professor A. Vijay Kumar sir and Professor Ramachandran Balasubramaniam sir, for gracing the occasion with their radiant presence and genius contribution to make this webinar a success. We trust that everyone present here must have immensely benefited from the same and its praxis in myriad fields. We would like to wholeheartedly extend our sincere gratitude to dynamic voice and seasoned Honorable Chairperson Professor Nageshwar Rao sir for his guidance and leadership and sparing time from his extremely busy schedule to grace this event of national pride. Thank you very much, sir, for sharing your inspirational and encouraging words on this important day with us like always. We would like to extend special gratitude to respected Professor Sujata Verma ma'am, Director School of Sciences, for providing all the necessary administrative and academic support to make this webinar a success. We also extend our sincere gratitude to respected Professor V.V. Subramaniam sir, Director, Center for Online Education, IGNOU, for live broadcast of this prestigious event on YouTube. We also extend our special gratitude to respected Shri Rajesh Sharma ji, PIU, IGNOU, for broadcasting the live event on IGNOU official Facebook page. We also extend our heartfelt gratitude to respected Shri K. Vishwanathan ji, Deputy Director, Graphic Unit, Electronic and Media Production Center, IGNOU, to design the beautiful poster of this webinar amidst his busy schedule. In the last, we extend our sincere gratitude to the respected faculty, members of the Seminar and Cultural Committee, School of Sciences, and the office staff who rendered their voluntary services since last few days to organize this webinar in a successful manner. Once again, thank you very much to each of the esteemed dignitaries for making it a success. Jai Hind.
Wish you all happy National Mathematics Day. A great thanks.
Thank you.
Thank you.
Yeah.
Thank you on my
Yeah,
behalf
thank you all.
to
Thank you all. Thank you
Director
all.
Madam and Seminar and Cultural Committee of School of Sciences, especially Professor Deepika and Dr. Vishal Warpa, to make this event a grand success. Thank you.
Thank you.
Many
Thank you.
thanks, sir. Many thanks. Yeah.
Thank you, Balu. See you.
Thanks. Thank you, Vijay Kumar.
Thank you. Thank you. Bye.
Yeah. Thank you, Professor.